Hello, I'm Mark Gorrith, and on behalf of my co-authors, I present our paper on scene-adaptive temporal stabilization for video colorization using deep video priors. Automatic image colorization methods applied independently to each video frame usually lead to flickering artifacts or propagation of errors because of differences between neighboring frames. Although several works attempt to solve video colorization problem as an end-to-end fully automatic task, most still rely on single-frame colorization due to achieving higher visual quality and naturalness. Temporal inconsistency appears when the same object has inconsistent visual content in the processed frames. As shown in this image, there are mainly two different types of temporal inconsistency: unimodal inconsistency, like the flickering artifact, and multimodal inconsistency, where we have possible solutions for a single input. For example, a car might be colorized to red or blue. Methods for temporal stabilization usually promote blind temporal consistency by means of dense matching, such as optical flow, to define a regularization loss that minimizes the distance between correspondences in the stabilized output frames. Such methods are trained with large datasets with pairs of grayscale inputs and colorized frames. In contrast, deep video prior or DVP can implicitly achieve such regularization by training a convolutional neural network. Such method only requires training on the single test video and no training dataset is needed. DVP proposed to select one mode from possible modes for the processed video and use this mode as a reference to ensure temporal consistency and preserve perceptual quality. Although DVP is a great proof of concept of using image-based operators on video data, it has limitations on real-world scenarios. The main limitation is the requirement to train in test time, which makes the method extremely time-consuming in practice. For instance, training depends on the content, motion, length of the input video, requiring a large number of iterations to generalize to complex sequences with multiple shots and scene changes. Moreover, as shown in the figure, a single main mode might not be enough for such complex scenes. In this paper, we propose a generalized framework for colorization of complex videos with an optimized few-shot training strategy to learn scene-aware video priors. The proposed architecture is generally trained to stabilize the input video and to cluster its frames with the aim of learning scene-specific modes. A few-shot training strategy is proposed to reduce the processing time of DVP due to training directly on test videos, achieving temporal coherence faster with the most representative few-shot examples per scene. DVP architecture is modified by adding classification subnetwork which clusters the input frames with the objective of learning scene-specific priors. Having the input image and its corresponding feature vector, the proposed model will generate a temporal stable output and a classification result, which at the same time will be used to generate the scene-aware embeddings that will be injected to each decoder block. Learning how to cluster the few-shot examples into different scenes will help the network to adapt in the test time to the whole input sequence, where some match frames between two scenes will generate softer scene-aware embeddings representing the both scenes. As mentioned before, the main limitation of DVP is the long processing time due to the need of training and inference time. This fact makes the method impractical for long scenes. This paper proposes to speed up the training process, reducing the number of iterations by means of a few-shot training strategy. The selection of n frames for few-shot training is based on a twofold process: scene segmentation and selection of representative frames per scene. Scene segmentation is performed in an unsupervised way by a subclustering of deep features with K-means algorithm, and an optimal number of clusters is computed for the given input video. After segmentation, suitable frames are selected from each scene by subclustering frames in that scene to cover a balanced span of different content. K-means is applied again with a fixed number of clusters, and number of frames is randomly sampled for each subcluster proportionally to the length of the subcluster. Following DVP baseline, an iterative regression training strategy is used to address the problem of averaging when the difference of multiple modes is large. In particular, a confidence map is used to enforce the selection of a main mode per pixel from multiple modes, while ignoring the outliers, which are minor modes leading to flickering artifacts. Then, a multi-loss function is proposed combining the RT loss with a cross-entropy loss for the classification subnetwork. Moreover, we propose a strategy for selecting the best main mode for RT training. As seen in the figure, a bad initialization, which an incorrect main mode, might lead to mode collapse. Finally, in this visual comparison, we have the processed frames, shown as frame-to-frame colorization, and three different stabilization methods: DVP trained for 10 and 50 epochs, and our method. As we can observe, our method achieved better fidelity and perceptual quality than the original DVP for 10 epochs, while taking less processing time. And the original DVP, trained for longer, takes primitive 38 minutes for training 50 epochs, but fails to generalize to multiple scenes, overfitting the process frames. Thank you for listening. If you have any questions or you want to connect, here I share my contact details, both from BBC and from social media. Thank you.